many of you might wonder what is really behind this kind of technology, and I like to kind of look at the Ampere processing element or the actual processors from a historical perspective, really looking at 30 years of developing processing silicon, going through this Hennessy and Patterson chart, which is a very famous chart, kind of. A lot of people talk about it as kind of the power behind Moore's law and all of that. But what everybody is seeing now is that the traditional way to scale performance has started to kind of taper off, which was Dennard scaling. This was a frequency scaling methodology that allowed us to kind of double performance as we increase frequency and decrease geometry in silicon manufacturing. But that started to tail off in about the 2010s. And now what we're seeing is that, yes, geometry still keeps shrinking, but the capability for us to get more performance out of it by increasing frequency has hit a bit of a wall. Because why? Because of power. And many of us take for granted the fact that we were getting this type of performance for many, many years because power was cheap and plentiful and nobody really thought about burning a bunch of it. But now we're getting to a point where that is actually unsustainable and we have to rethink this. So this is where Ampere entered the picture. Ampere entered the picture 6 years ago and we took a different path. As you can see on the chart on the left, there's a red line, which is the thing that's still scaling on that chart, and that is core count. Core count is still scaling because geometries are shrinking, albeit a little slower and a little more expensive, but they are scaling, and that's the way that people are getting more performance. Multi-core processors, whether you're processing video in a VPU, as Mark introduced, or you're processing graphics and GPUs or AI in whatever accelerator that you're using, also the same for general purpose processing. Now, if you look at this from a historical perspective, the idea of multi-core and running multi-core at a certain point in the thermal and frequency curves of modern processors. This is how you get power efficient scaling, by designing cores that are very, very consistent in performance and also very low power individually, but scaling them out to a much larger number. And if you do silicon design this way, if you do processor design this way, you can end up with a much more power efficient architecture, which is exactly what Ampere has done. And to the tune of, somewhere in the neighborhood of about 4x better power efficiency, if you measure performance from like how much work can I get done on this processor, divided by how much power does it cost me? That's the efficiency. Then Ampere can give you up to 4x better profiles. I'll show you that in just a moment. But some other comments, along the way, along this journey that the Hennessy Patterson, chart shows, there were a lot of things that came as baggage in this industry, from turbo frequency to hyperthreading to scale up acceleration inside the actual processors. Again, because power was plentiful. Nobody cared if you burned a few extra watts back in the 90s or in the early 2000s. If you burned a few extra watts by boosting the frequency through turbo, great. You got a little bit of extra performance out of that. Hyperthreading was stuck in there to actually kind of maximize the efficiency of an underutilized core. But today's cloud atmosphere has changed radically. We're looking at compute elements that are very, very utilized. In other words, they are utilized constantly and at a consistent rate. And many times you've got this kind of spiking and scaling that happens. And software technology has evolved to be able to take care of that, to be able to scale and elastically allocate capacity through very innovative technologies like Kubernetes and containers and all this kind of thing. But this is the way that you get scaling performance through scale out. You're provisioning along a lot of cores, and the code is written to take advantage of all of those cores so that you get consistent and very predictable performance out of that architecture.